And so that's very much a work in progress. I know people say that quite always, basically, but in this case, you'll see it's real. So it's gonna be different from what the paper is meant to be, or will be, hopefully. So in the paper, what we want to do is to lay out the rules that are that have been developed by the quantum information community, and to see to see whether it's possible to describe some of the axioms that they designed, and to describe some of the laws they are thinking about in more physical ways, or in more what we're going to call phenomenological way. And I'm going to be more explicit about that. But today we are not going to do that since it's a work in progress. But we at least want to motivate this whole project. So we hope we are going to convince at least some of you that it's something worth pursuing and worth doing. Also, let me say, we're going to be there's going to be somehow an anomalous talk with respect to the stuff we've been doing the last days. So we're not going to talk explicitly about computation. So the focus is going to be more about quantum information. And as Alberto said, I'm a metaphysician, so you're going to hear some weird, crazy stuff about information and fundamentality. So I hope you will enjoy that. Okay, I think we can start. So that's a very nice quote from Asher Perez from 2006. He says, quantum phenomena do not occur in a Hilbert space, they occur in a laboratory. So that should look rather trivial. I mean, you should wonder why anyone would even think about saying that. But you also know that very often in quantum mechanics, what happens is that people, to describe the theory and to describe the properties of the theory and what's important to know about the theory, they're going to start with Hilbert space formalism, the property of the Hilbert space. So it looks like really the experiences and the experiments we did, which were very exceptional and astonishing, just come at a later stage. But it's also trivial that the very reason why the Hilbert space formalism works so well is precisely because it fits well with those experiments. So we should remind ourselves this all the time. So when it comes, what's not trivial, let's say, what is less trivial, is that when it comes to quantum mechanics, and that's different with respect to other theories, when it comes to quantum mechanics, it's very hard to say how the formalism relates to the experience, to the physical world. That's just restating what the main problem with the theory is, according to many people. And of course, one way to try to address this issue is to say, well, then the formalism is not correct, or it's not complete. We should change the formalism. And people have tried basically each of the options I just mentioned. Some other people, which are the people we're going to engage with today, instead thought, well, it's not the formalism the problem. Maybe the problem is that we should rethink what we are asking from a theory that fundamental as the quantum theory. Maybe we should think that this is a physical theory, but in a sense that we didn't meet so far in the history of science. And one way of doing so is basically to claim that quantum theory is about information in a sense that it's yet to clarify. And then we don't have to commit to any specific ontology, at least at this stage. We are going to say that quantum mechanics is about information, and the only sense in which we can talk about stuff is by explaining how experiments relate to gathering, manipulating information. So we are going to focus on this subset of people in the quantum foundation community. And what we're going to do is to try, again, as I said in the introduction, to try and say how far do they go in providing what we call a phenomenological descriptions of the rules to gather and manipulate information. We're going to focus on one approach that was developed by Dariano, Chiribelli, and Perinotti, and Richard is going to introduce the approach. And we will see that they basically found 6 axioms from which they recover quantum theory. And what we want to say is that we should hope that those axioms are somehow related to the phenomenological experience. So that's the outline. First, Richard is going to present the framework. So that's going to be the technical part. That's also why Richard is going to do it, because I can't. And then I'm going to come back and talk about what we mean by phenomenological description of a law. We're going to give a sort of a definition, and hopefully, we can refine this definition with your help. And then finally, we're going to tell you very little about what we should do in the real paper, in the paper we are going to work on. So I'm going to leave the stage to Richard.
Hello. Okay, so as Cristian has just talked about, I'm now going to describe the mathematical framework behind this informational description of quantum mechanics. So to begin with, it's all about the operational principle. And these are broadly called operational probabilistic theories. And that'll become clear as time goes on why it has that name. So really at the heart of it, you have the fundamental things you want to deal with if you're going to talk about information retrieval is experiments. To this point, we have things like systems, tests, outcomes, probabilities, and states, effects, and transformations as the core elements. And then to give you an example of what they mean in a context, you can think of something like a Geiger counter. And the system it takes in terms of an experiment, is some particles. The system it outputs, you can think of as a sound or not. And that's the outcomes that can come from that. And the probability of that happening is related to the probability of detection by this particular test. And on top of that, you can think of state and effect as the start and end points of an experiment. To understand that in advance, in case it gets confused later, you have a general thing as a transformation that takes you from one system to another. But if you wanted to sort of describe your experiment fully and say it began here, it ends here, these are sort of trivial initial systems that become states, and tests or effects or measurements, as they might be called variously, are systems to a trivial system. And you'll see that diagrammatically to come. On top of this, with states, effects, and transformations, you have their types, which are atomic, pure, and mixed, and completely mixed. These do map to what you're imagining from quantum mechanics, if you know something about that. However, they are not introduced in that way, and that's certainly not how they're axiomatically presented. So pay attention to that in particular as it comes. We will focus, as Cristian said, on Kirabella, Mariani, and Peranotti's approach, and their definition, succinctly. An OPT is specified by a collection of systems closed under composition, and by a collection of tests closed under parallel and sequential composition. And that should become clear as we move to the next slide. So an important feature of the OPT framework is there is a categorical underpinning. Specifically, it uses symmetric monoidal categories, or more specifically, dagger symmetric Frobenius algebras, should anyone out there care. Now, the key thing about this is this has a natural mapping to diagrammatic structure. And this gives the formal meat behind a lot of the interesting equations you see, or entirely diagrammatic proofs that you'll see in this area. But moving specifically to what we had at hand, the test, that was the core element, the core thing of an experiment. And we describe it here as essentially a collection of events. So here we have CI is an event that takes things of type A to things of type B, and there's a set of them, and that's what makes this a test. If we move to the next slide, I'll talk to you about what they are. So here we have individual events. This is unsurprising. A test is a collection of such events, and an event is described similarly to a test. Along the lines of this, you can view an event or transformation that goes from the trivial space to a system, or from a system to a trivial space, as preparation and observation, respectively. Also termed as an effect with respect to observation. The literature moves around on these definitions. Okay, so we have this diagrammatic structure. On the next slide, I should be able to talk to you about the composition that I mentioned. It is probably unsurprising that an event that takes in A and outputs B can then be attached to an event that takes in B and outputs something else. So it goes from A to B to C in a natural way. Parallel combination of events is pretty much as you see it. You have an A and a C system. And obviously by composing two tests or events, you can go to B and D. If we move to the next slide. So it's not enough just to have this structure of experiments, though. We need to bring in probability, especially if we're going to talk about quantum mechanics. Now, there's a bit of mathematical meat here, but don't focus on it if you're not particularly interested, because I will summarize it briefly in the next slide in a diagrammatic way. But what we need is basically every map from the trivial system to itself, which is what all total experiments are, right? You start with a state, you do some things to it, and then you measure or observe or apply an effect in this literature at the end. And that should equal probability in terms of a particular transformation. And over all the transformations, it should sum to 1, because the probability of getting something should be 1. If we move to the next slide, I can show you how this is diagrammatically. So, as described, if you have a state rho I is created, and this is of a system type A, and then we have a measurement of AJ applied, then the probability we get is Pij, which is just referencing. That's the chance of that string of events occurring together, given some particular test. The composition of probabilities is the multiplication of these, which makes sense. If the top one is about the chances of these things happening, then obviously if we have this happening and then some other test at the same time, the chances of them both happening are going to be the combination of those probabilities. If we move to the next slide. Okay, so we've talked about the general setup. We've talked about how probabilities come in. Now, purity and mixedness are defined rather differently to the way they're usually introduced in quantum theory. You might be able to see the parallels if you're particularly sharp, but I think you'll agree it's quite a different approach. So given two different tests, DJ and CI, the former is a coarse graining of the latter if there is a disjoint partition as described on the slide. Don't look at that too much if you're confused by such things. We can reduce it to a more understandable terminology by thinking, okay, if the situation was what's in my bag, that's the experiment at hand, I've had a sack of things. You look inside and you say, well, I see a cat, a llama, and an apple. That is you giving, if you want, an atomic, which is a term I'll describe it more formally later, atomic description of what's in the bag. You name 3 distinct items that couldn't be subdivided. However, you could coarse grain this measurement. You could say, okay, well, I have animals and I have an apple. It's the same thing, but ultimately you can see it's less well-defined. And this is if you like, in this case, it's a mixed measurement. You gave a measurement that could be more specific, more refined. If we move to the next slide. Okay, so some of the terminology I brought up clarified. A transformation C is atomic if its only refinements are what is essentially their trivial. Mathematically, it's just saying you can partition it in no meaningful way. This notion of refinement is what allows for pure and mixed states. A pure state is an atomic state. A mixed state is a state that isn't pure. And a mixed state is completely mixed if any other state is its refinement. Now, this is perhaps a little bit obscure if you're coming across this for the first time. And I thought about different ways to present it. And I actually think turning it around and talking about a completely mixed measurement might make more sense. So going back to my bag example, if the experiment is what's in the bag and I'm your measurement and you say, what's in it? And I say something. You have learned absolutely nothing. I've given you a response. It contains all possible responses, but you have learned nothing. And in that way, that's a completely mixed measurement, which is sort of the converse of a completely mixed state, which is defined analogously, but doesn't have quite as good a intuitive description. So moving on to the next slide, let's move to the axioms. So I've given you the framework. I've given you the structure of operational probabilistic theories. Now, these axioms that I'm going to present now are sufficient to give you finite dimensional quantum theory, as proven by Dariano Perinotti and Kirabella. We won't go into the details of how that goes down, as it's quite an extensive proof and relatively mathematical. But I would encourage anyone who's interested to look. Indeed, I'll be going through these postulates quite quickly without too much reflection on the mathematics. But we can always go back later if you have questions. And on top of that, there's the paper, which is excellently written and is there to be looked at. Okay, so on the point about matching quantum theory, we have this lovely quote. Quantum theory can be derived from purely informational principles. In particular, it belongs to a broad class of theories of information processing that includes classical and quantum information theory as special cases. Within this class, quantum theory is identified uniquely by the purification postulate, stating that the ignorance about a part is always compatible with the maximal knowledge of the whole in an essentially unique way. This postulate appears as the origin of key features of quantum information processing, such as no cloning, teleportation, and error correction. So with that in mind, let's move to the axioms. So the first one is, I guess, unsurprising if you think about it. It's causality. Now, the point here is that any preparation you make, its probability of occurring, the different events that could occur, should have no dependence on a measurement later applied. It's basically stopping past from influencing now. Future from influencing now. And the mathematics here just talks about marginal probabilities and how the marginal probability of generating particular states is independent of what's later applied to them in terms of measurements. Okay, moving to the next slide. So perfect distinguishability. Every state that is not completely mixed can be perfectly distinguished from some other state. So this is pretty much exactly what it says on the tin. If you have any particular state in your system, there is some measurement you can find that can tell you exactly what it is. Okay, moving to the next slide. Ideal compression is slightly more complicated in its presentation, but is relatively simple once you get to it. For every state, there exists an ideal compression scheme. Okay, a compression scheme is lossless and compression scheme that is lossless and maximally efficient is ideal. What's a compression scheme? It is a test from A to a smaller system C, and we view that compression as lossless if, in a sense, it can be inverted by a decoding operation. So you can imagine you have some system, you have some things in a bag, and you transform them, and then you untransform them. If there is a way of doing this such that you get the original states back, you're not confused, you haven't lost any information, that's where the lossless comes from, then that was a lossless transformation and a lossless compression scheme. Now, a lossless compression scheme is maximally efficient if the encoding is as small as possible. You basically have as little redundancy and no redundancy. Then it's viewed as maximally efficient. So this axiom really says that for every state, there exists such a compression scheme. Moving to the next slide. Local distinguishability, which is an interesting one, and I'll tell you why. If two bipartite states are different, then they can give different probabilities for at least one product experiment. Now, if you look closely at that diagram, you have a bipartite state on the left and another bipartite state on the left in terms of rho and sigma. And you notice that what we're saying is you can detect their difference by local measurements. We didn't require a bipartite measurement to see that they weren't the same. And as Cristian will mention later, if we have time, you can view this as relating to the fact that you can know something by local experiments. And it's actually quite a devastating condition if you don't have this. It would mean any sort of bipartite system would require a bipartite or multipartite measurement. You could never really know anything locally. Okay, and with that, I move to the next slide. Pure conditioning. This is a relatively simple one in that if you have a bipartite system in a pure state, then the outcome of an atomic measurement on one side just creates another pure state. In a way, this is saying that you can't get to mixedness. You can't get a lack of refinement without using something that is unrefined. Atomic pure things will only produce atomic pure things. Moving to the next slide. So this is the purification postulate, and this is perhaps the one most of interest to those people interested in quantum mechanics and how special it is. Every state has a purification. For fixed purifying systems, every two purifications of the same state are connected by a reversible transformation on the purifying system. Now, not focusing too much on the reversible transformation, but looking at the overall notion of purification, what does that mean? It means if you have any mixed state, you can, in the usual language of Hilbert space quantum mechanics, go to the church of a larger Hilbert space and find a pure state with a mixed measurement applied to it that will give you that state. This is a one-to-one correspondence with that notion, essentially. But here it's specified without any particular reflection on mathematical principles or spaces or things that don't have a phenomenological meaning in terms of being a test or an experiment. And with that, I now move to Cristian again, I think, since this is the end of my section. I hope that wasn't too quick for everyone.
Al, can you tell me how much time do I have, roughly?
Roughly 6 minutes.
Oh, well, we started a bit later, so I'm going to.
Yeah, you can talk like 10 minutes.
I'm gonna try to be quick. Anyway. So just to recap, what we said, I was saying in the introduction. So I was saying that physical laws in non-quantum physics, let's say, to be very rough, can seemingly can be stated as universal claims about things that we meet in the three-dimensional space. So I'm not going to mention examples, but the idea is that you can always refer to everyday experiences, even with relativity, to explain what those laws are about. And it looks like in quantum mechanics that's not so easy to achieve. That's one of the problems we have with quantum mechanics. So the axioms that Richard just presented are, as he was saying, are meant to provide a framework for reconstructing any theory that is called quantum, that's supposed to be quantum, so quantum mechanics included. So the idea now is that since, as we were saying, the only way in which those axioms can be connected safely, let's say safely, can be connected to anything phenomenological is via experiments, via information gathering, information manipulating through experiments. That's basically what also Richard was talking about. That, if anything, that's what there's phenomenological there. But then there's a conceptual issue there that has been, of course, debated by physicists and philosophers that is very broad. And of course, we are not going to address this too much. But the idea is that it cries for an explanation how information relate to things. So if you look at the literature in the last decades, there are a lot of weird claims. I'm going to say weird, but maybe they're actually nice, fine. But sometimes you find claims like, quantum theories are not about things, they're about information. So one of the authors of the work we were mentioning, Mauro D'Ariano, I think it'd be okay if I quote him on that. He said that stuff at least hundreds of times. And it's clear that there is some idea there, but it needs to be spelled out in more details. That's clearly so. So if you assume also, besides this idea, you also assume that quantum theory, not quantum mechanics necessarily, but quantum theory is somehow fundamental in the sense that any theory is going to be quantum, then we can understand further claims like, it from bit made from Wheeler, it from qubit, which probably was Seth Lloyd, I might be mistaken, or software without hardware and stuff like that. Now, there seem to be two approaches there that need to be distinguished, and Lediman and Ross did very carefully that in their book, Everything Must Go. They distinguish between an info stuff approach and an information theoretical approach. So the first one is the idea that physics ultimately talk about information as the ontology, as what's ultimately out there. On the other end, let's say the more weaker approach is to simply claim that information theoretic tools can help us understanding better physics. So now, what's interesting here is that if we assume, in part for the sake of the argument, in part because some of those people who developed those approaches, Richard introduced, the stronger claim, then we might want to still try to provide a phenomenological understanding of those laws. And the reason is the following. So if we take the debate between the it from bit, the new people saying it from bit, and the most conservative people that say the opposite, that the bit comes from the it looks like what they're really debating in order for this debate to be interesting is not about what exists. It's not about, nobody's denying that there are things, I hope. Some of them probably are rightly so, taking this debate as about what is fundamental. So the idea is that we should focus on the from preliminarily in order to understand how those people are, what those people are debating about. So focusing on the from means if you take an example of a chemical state like a molecule, and we say, well, a molecule comes from a certain configuration of atoms, we see that the from clause in this statement is meant to indicate what is more fundamental, what depends on what. So it happens to be the case that in the metaphysics that sometimes it's, I hope it's useful, there's been a huge debate on how we should individuate those relations of priority. And one thing that when I started discussing with Richard and started getting interested in this debate is how little people try to use those many notions to make sense of the claim that it comes from bit. I'm not saying that everyone did so, but a large majority didn't seem to clarify what seemed to be going on there. And I think, if we look at the many notions that have been developed in the recent history of metaphysics, I think we can start to ask questions about relations of dependence of whatever fundamental is according to the quantum information community with respect to the level of reality in which we seem to live and in which we make experiments that, again, are those described by those axioms. So, again, I'm not going to mention the people that developed those notions. I'm going to say something at the conclusion about which of those notions I think is most promising in this context, provided some of you is interested about that. But again, the idea is that in the case of it from bit or bit from it, what the debate is about again, what the relation of priority, the direction of the relation of priority. But again, so understood, it looks like neither claim, nor the classical, neither the classical nor the it from bit one, can refrain really from addressing a more important issue, that is how exactly those two levels relate. So again, if you go back to the example I was briefly mentioning about the chemical state and the configuration of particles, that it looks like in the history of science is considered a success whenever we were able to establish that one level, so let's say a certain ensemble of descriptions and of laws can be derived from another one. And it doesn't mean, the fact that we can derive, for instance, chemistry out of physics doesn't mean that there is no level of reality that corresponds to chemistry. We do not want to eliminate from the word molecules. We just want to say that they can be explained in terms of something more fundamental. And again, that's something that is usually taken as a success whenever it's done. So one of the claims we want to make is that in the case of it from bits, as probably you already understood, we believe we shouldn't make an exception here. We should, again, believe that this claim, if understood correctly, and if we are able to explain exactly what this relation of priority means, we are, after all, explaining something about the physics that's behind. Unless, again, this is meant as an eliminative claim, in which case the idea would be that there is no it, really. There are no things. There is just software. And in which case, however, I think this can be contested, but it wouldn't make much sense to me. So you can see that as a priority claim, this claim should both explain how the whole information, how everything emerges from information quite in general, and that's a quite difficult task, of course. But I think more importantly and more interestingly, one should be able to explain how, from a certain set of bits, for instance, one can have as an emergent phenomenon a certain configuration of particles instead of another one. So the details of that, I think, might be interesting. And again, if we assume that the laws that are about information are going to explain the laws that are about the things, we would thereby know that the constraints about the laws, the constraints that we put about the information, the info laws, the laws about information, are going to put constraints on the laws about things and how things behave. So let me be quick about that. So the idea, again, is that if the only thing we can say about those laws is that they talk about experiments, then we have to be able to provide certain generalizations about experiments that are made in the ordinary space, and try to see where those generalizations about the experiments are grounded or explained based on the theory, on the derivation that we are looking at. So we believe that one way of doing so, of translating between the two levels, is by focusing on what we call the phenomenological description of a law. That definition is really an attempt of a definition. We know there are problems with that, but the idea is that there are certain criteria that this description should meet, and they are the following. So first of all, again, this phenomenological description should be about things in three-dimensional space, and the reason is simply because that's where we make experiments. It should be suitably generalized depending on the context, but it has to be generalized. And it has to describe facts at a certain derivative level of reality. Again, because experiments are at a derivative level of reality, they don't seem to be a fundamental kind of entity in any sense. And finally, that's important, that's where the priority claim lies, the truth of the phenomenological descriptions, the truth about facts about the phenomenological description should depend on the truth of more fundamental facts about information, let's say. Okay, so the idea is that now that we have, and I'm going to conclude, now that we have this definition of a phenomenological description of a law, I think we have motivated in a sense why we can look for a redescription of those axioms and to see whether they can be made phenomenological in the sense that we just introduced. There are two main tasks there that are the tasks we are working on, and we have some ideas, but we're not going to go too much into details because it's so late. So basically, the two tasks are first to find what the corrective relation of priority is in this case at n, because again, they're not the same, and one of them might be preferred instead of another one. And finally, that's more important, we have to show for each of the axiom whether and how they have a corresponding phenomenological description. If we do that, of course, we're not showing that the it from bit claim is true, but we are showing how it can make sense. So, and we're also showing how those axioms can refer to, as other standard theories can refer to the world we live in. So I'm going to skip that because it's late. But again, if you want to ask, of course, for instance, for causality, that's, as also Richard was suggesting, that's going to be rather straightforward, and it's going to be a substantive issue whether these axioms, also a metaphysical issue, whether these axioms should come true. So the idea is that all information that determines the outcome of an experiment is in the past of the experiment. You can see that this definition, this reformulation of the causality axiom seem to match all the criteria we have introduced about the phenomenological description, because in 3D space and all the other three. So I'm gonna, it's very late, so I'm gonna stop here, and thank you for listening.